First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Here's the season to be serving.
When I was solving equations, I was feeling amazing.
All right, greetings, welcome back. And this is the DISC method part 2. In the DISC method part 1, we found the volume of solids of revolution, which were revolved about the x-axis. And the formula here gives how we did it. It's a very basic formula. The volume is simply pi times the integral from a to b of the function squared, the function f of x, which is being revolved about the x-axis. The difference today in the part 2 video is the function is going to be revolved about a horizontal line other than the x-axis. So a horizontal line of the form y equals k is going to be the axis of revolution, this case. And we're going to kind of see how that changes things. So to understand that, let's take a look at how we did it in part 1. So this is an example of what we kind of looked at in part 1. So here I have some curve, f of x is 5 sine of 0.5x. And I got it going from some interval a to b. And here you can see the function as if we're finding area under the curve, like we're finding the definite integral of the function from a to b. And what we did to revolve it about the x-axis is when we revolved it, it created this three-dimensional figure. And what we concentrated on in part 1 was finding the volume of that three-dimensional figure. Okay, so what's going to be different today is, as you can see here, this function is being revolved about the x-axis. This is the x-axis here. So what is going to change is we're going to revolve it about some other horizontal axis, some other horizontal line of the form y equals k. So the question is, how does that change our formula? Remember, our formula was simply pi times the integral from a to b of the function squared. And the reason that was our formula, just to take a sneak back to what we did in part 1, what we did to find this volume is we essentially chopped this three-dimensional figure up into an infinite number of slices, and each slice represented a right circular cylinder, which we called a disk. And you know, the volume of a cylinder is pi r squared h, and h was delta x, and r, so if you look at any point on this particular function, r is simply, let me go back to 2D for a second, the radius is simply the distance from the end of the function to the x-axis, which is simply the value of the function at each given point. And so that's why in the formula we have f of x being squared, because f of x is going to represent the radius. But if I'm revolving the object about a line other than the x-axis, how does that affect my radius? So let's take a hypothetical. So let's say from this point to the x-axis, that distance is 10. So we're just going to say that this distance is 10. So when getting this point, the radius at this particular point is 10. And that's the distance from here to the x-axis. But what if I choose another horizontal line as my rotating axis? Say, for instance, I choose the line y equals 1. Now look what happens. Instead of going all the way down to the x-axis, it goes down to 1. So before, the distance from here to the x-axis was 10, but since I'm not going to the x-axis and I'm only going to 1, so now the distance is 9. It took 1 off what the previous radius was. And I don't have to go short of the x-axis. I can even go beyond the x-axis. Let's say, for instance, I want to rotate about the line y equals -2. So if you notice here, it goes 2 units below the x-axis. And so again, if this radius from here to here, from here to the x-axis was 10, so the new radius now is 12. 10 and then the 2 units below the x-axis. So how does that work in our formula? Well, if you think about it, when the radius, when the axis of symmetry excuse me, not the axis of symmetry. When the axis of rotation was 1, the radius we were looking at went from 10 to 9. So that's the function minus 1. 10 minus 1 is 9. And when the axis of symmetry was -2, the radius went to 12. Again, that's the function minus -2. So 10 minus -2 is 10 plus 2, which is 12. So if you look at it, to find the volume of a solid revolution where the function is revolved about a horizontal line, say y equals k, all you have to do is find the integral of f of x minus k squared. So again, the formula is the radius squared. When we went about the x-axis, the radius was f of x. Well, when I go about some line y equals k, the radius is now f of x minus k, just like when it was 1, 10 minus 1 was 9. When it was -2, 10 minus -2 was 12. So our formula looks like this. So this is how the new formula looks like in this case. So it reads, to find the volume of a solid revolution with a function f of x rotated about a horizontal line y equals k from x equals a to x equals b, we use this formula. And you can see the difference is we're taking f of x minus k squared versus just f of x squared. We still have the pi. Everything else is the same. The only difference is we're going to do f of x minus k squared. Now, a point of this that I want to point out, which is going to become a little bit confusing when we do something called the washer method, is in this, again, remember what's in here is the radius. We're squaring the radius. So when we went to the x-axis, the radius was just f of x, or you can even think of it as f of x minus 0, because the formula for the x-axis, the equation for the x-axis is y equals 0. But when I go to, when k is not 0, you know, it's going to be f of x minus k. But the point I want to bring home is it's f of x minus k whole squared, not f of x squared minus k squared. So if you just think about the foundations of, if you just think about the underlines of this particular scenario, again, what's being squared is the radius. And in this case, the radius is the function minus k. So therefore, it's f of x minus k whole guy squared. That's important to remember, because again, we do something called the washer method. Just to give you a preview, the washer method is going to be like f of x squared minus something else squared. So that's just very important not to get those two confused. So let's go ahead and look at a couple of examples. So here's the first example we'll look at, and it says find the volume of a solid generated by revolving the region bounded by the graphs of y equals x, x equals 0, x equals 2 about the line y equals 4. So in this case, we're revolving the function y equals x about the line y equals 4 as x goes from 0 to 2. So let's go ahead and work this out and see how it looks. All right, so here's the situation, my guy. So this is my f of x, this is my k. So the volume thus is going to be pi times the integral from 0 to 2 of x minus 4 squared dx. So that's what I need to integrate. So again, it's not x squared minus 16, rather it's x minus 4 squared. So I like to go ahead and span this before I integrate. So this will be pi times the integral from 0 to 2 of x squared minus 8x plus 16. All right, there's a function there. And I see my pen perhaps going out on me. So let me already get ready for the change. So as I change pens, I'm changing colors. It's still all good in the neighborhood. So let's go ahead and find, let's go ahead and integrate this guy. And this would be pi times x cubed over 3. And that's what we get for x squared. And for 8x, we get 4x squared. And for 16, we get 16x to be evaluated from 0 to 2. So all we need to do is plug in 2, because plugging in 0 would just be 0. And so if I plug in 2, this is pi times 2 cubed is 8. 8 over 3 minus 2 squared is 4 times 4 is 16 plus 2 times 6 is 32. So we'll have positive 16 here and 8 over 3. Let's continue the arithmetic. So again, the sum of these two guys are going to be 16, and then you have this 8 over 3. So this is pi times 8 over 3 plus 16. And 16 is 48 over 3, so this is pi times 8 over 3 plus 48 over 3, which would be 56 over 3 pi. All right, so that's how that first particular example goes. Again, you know, it's a pretty basic transition from the basic disk method to this particular disk method. So when I say basic disk method, I'm talking about revolving about the x-axis. So the only thing here, I'm revolving about some line y equals k. I'm just going to do the function minus k squared. There's a little expansion there if you want to expand before you integrate, but other than that, it's pretty simple. We call it pretty vanilla. Let's go ahead and look at another example. All right, so in this example, find the volume of the solid generated by revolving the region bounded by the graphs of y equals negative 3x plus 7, x equals 0, x equals 3, about the line y equals negative 2. All right, let's dig into this guy. All right, so here's the situation at hand. So the volume is going to be pi times the integral from 0 to 3 of negative 3x plus 7 minus negative 2 squared dx. So that's our particular situation. And you can see that this 7 minus negative 2 is turned to 7 plus 2, so that's going to turn into negative 3x plus 9. So this is pi times the integral from 0 to 3 of negative 3x plus 9 squared. I almost forgot the fact that this is being squared. Not sure how I forgot that. So I'm going to go ahead and expand this, and then, of course, integrate the guy. So when I expand this, I should get, so pi integral 0 to 3, I should get 9x squared minus 54x plus 81 dx. All right, so let's go ahead and integrate this guy. So the integral of 9x squared will be 3x cubed. The integral of 54 of 54x will be 27x squared. And 81 is 81x. That will be evaluated from 0 to 3. Good news, we got another 0, so all we have to worry about plugging in is 3. Let's go ahead and plug in this 3 and let's see what life gives us. So this is pi times, okay, 3 cubed is 27 times 3 is 81. And 3 squared is 9 times 27 is 243 minus 243. And 3 times 81 is 243 plus 243. So that worked out for pretty easy arithmetic. And so the 243s are going to cancel themselves out, and we're left with 81 pi. All right, let's do one last example. Again, this method, part 2, finding the volume of solids of revolution revolved about horizontal line y equals k. Example number 3. All right, so in this final example, find the volume of the solid, I misspelled solid, please forgive me, formed by revolving the region bounded by the graphs of f of x is 2 minus x squared and g of x is 1 about the line y equals 1. Now, if you notice, there's no limits to the integral. It's no x equals this or x equals that. So we don't know what to integrate between. So when we get the situation, and it's similar to what we did with area between curves, when we get the situation where they don't give us the intervals in which to find the volume between, we see where the two functions intersect. And so notice in here they gave us the graph and the region bounded by these graphs. Now notice g of x equals 1 is also the line we're rotating the graph about, but it made sure to mention that we're looking at the region bounded by the graphs of this guy and this guy. So I want to see where those two intersect, and those are going to give me my limits of integration. So let's see where those two functions intersect. So of course, to see where two functions intersect, we set those functions equal to each other and we solve for x. So I prefer the x squared to be positive. So I'm going to move the x squared and the 2 to the other side. And so that's going to give me x squared, and then there'll be a -2 and a 1. So x squared minus 1 is 0. And so this is x plus 1, x minus 1. So the intersection is plus or minus 1. So we're going to be integrating for plus or minus 1 of the given function. Now, when we set this function equal to 0, because again, remember, we have to do the function minus the other function squared. When we set the function equal to 0 here, we essentially were subtracting the two functions. So we're subtracting f of x and k. Now, technically, this was k and this was f of x. So technically what we did is we did k minus f of x versus f of x minus k. But that order doesn't matter because the guy is being squared. For instance, f of x minus k squared, well, that's f of x squared minus 2k f of x plus k squared. And if I did k minus f of x squared, I would get the same thing. I'll get positive f of x squared, then I'll get a minus 2k times f of x, and then I'll get a positive k squared. So, I mean, if you look at it numerically, 3 minus 5 squared is the same thing as 5 minus 3 squared. So the point I'm trying to make is the fact that this is k minus f of x versus f of x minus k doesn't matter because it's being squared anyway, and it's going to end up being the same. So this is the difference of f of x and k. So this is what I'm going to square. All right. So I'm trying to integrate. So the volume, rather, is pi times the integral from -1 to 1 of this guy right here, x squared minus 1 squared dx. All right, so let's go ahead and expand this. So this is pi integral -1 to 1. This is x to the 4th minus 2x squared plus 1 dx. And so that's going to be pi times x to the 5th over 5 minus 2x cubed over 3 plus x from -1 to 1. All right, the bad news is we don't have a 0 limit, so we have to plug in both numbers. But the good news is these numbers just change in sign, and each exponent is odd, and they're going to end up being subtracted. So really, in essence, what's going to happen, I'll write out each number, but really what's going to happen, whatever value I get for plugging in 1, that value is simply going to double. Again, because these are polynomials being raised to odd powers, and I'm putting in -1 after I put in +1. But let's go ahead and just do the math. So this is going to be pi. So when I plug in 1, that'll be 1/5 minus 2/3 plus 1 minus. And when I plug in -1, that'll be -1/5 plus 2/3 minus 1. Probably should have put this in brackets, but we're fine. So if you notice, and this is why I'm saying everything is going to double, you're going to have 1/5 minus -1/5. That's 1/5 plus 1/5. You're going to have -2/3 minus 2/3. Again, that's doubles, and 1 minus -1. So everything's going to double. So this is going to be pi. And so that doubles to 2/5. This guy doubles to -4/3. And this guy doubles to 2. And so we need a common denominator. That common denominator would be 15. I think I have room to put this in here. So this is pi times, this guy needs to be multiplied by 3/3, 6/15, minus, this guy needs to be multiplied by 5/5, 20/15. And this guy, of course, is just 30/15 plus 30/15. And you can see here, if you take these two, that'll be 10 plus 6 will be 16. So that's going to be 16 pi over 15. All right, so that's going to conclude this particular lesson on the DIS method part 2, revolving f of x about the horizontal line y = k. We'll see you next time.
Specialize in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe-to-toe, impeccable, splitting your back, son, simple as addition and subtraction, black thought, the infinite relax one.